Welcome back to CS Connect series. In Mathematics for Computer Science content, the first playlist that we are going to enter is set theory. This video will cover all the basic concepts of set. What are actually sets? In this diagram, you can see there are lots of stars available. We can call them as an unordered collection. You don't know which star comes first and which star comes next. But overall, all are put together under the same name called sets. Here, every star is called as the element of the set, or we can say member of the set. How do you represent a set? We actually use curly braces notation to represent sets. Now we will just translate this abstract definition to a particular example. Let's take a set of vowels. What are the vowels available in English alphabets? A, E, I, O, U. Take this to be a set V, and inside V you have 5 elements called A, E, I, O, U. How do we actually describe sets in the form of mathematical expression? We can do that in two ways. The first way is the description using a roster method. If we take the set of vowels A, E, I, O, U, if you represent using this curly braces method stating what are the elements alone, that will be the roster method. When you take the next example, set of odd positive integers that are less than 10. So from 0 to 10, what are the odd integers that are possible? 1, 3, 5, 7, 9. So we are representing it as set O is equal to 1, 3, 5, 7, 9. So when you use the curly braces notation in order to specify the elements present inside the set, that is called as the roster method. The next method is the description using set builder notation. Here you will not specify the elements exactly, but you will say a description about those elements. If we take this particular set O, here you can describe this as x is an odd integer less than 10. If you want to translate this into set elements, you can just take 1, 3, 5, 7, 9. So they are less than 10, at the same time they are odd. When you describe sets in the form of set builder notation, you will not focus on the elements, but you will focus on the description of those elements. But in roster method, you are not bothered about the description, but you are only concerned about the elements that are defining the set. This is like x such that x is an odd positive integer. This is how we'll be translating in English. So here x is an element of set O. How do you represent this? You have to use the belong to notation. How do we represent when we say that x is not an element of set O? So from this we can say 2 is not an element of set O because it is an even integer. In that case, we denote it as x does not belong to O. All sets are assumed to belong to some fixed large set called the universal set. So there is a universal set, and inside this universal set we are placing whatever sets we have taken as examples here. Given a universal set and a property, if we take this particular set O, what is the property of this set O? Set O has elements that are odd as well as that are less than 10, specifying the universe as the set of positive integers. So if you take a rectangle like this and you say all the integers are inside this particular universe, we can represent this as set O is equal to x belongs to the set of positive integers because it is mentioned as z plus. So I will tell you what are the notations of integer rational numbers later, but you have to represent positive integers using z plus such that x is odd and x is less than 10. This will state what the universe is about. Using this property, you have to choose the elements from the universe. From this we can say 1, 3, 5, 7, 9 can be picked up as a set, and this set is named as set O. So when you represent a rectangle and inside that when you represent a set, it means you are specifying the set along with the universe. Next we'll see about Venn diagrams. What are Venn diagrams? They are pictorial representation of sets. A rectangle is used to indicate the universal set U. Inside the rectangle, we will draw a circle to represent the set with the elements. So let's take the set of vowels A, E, I, O, U. Let's take the universal set and we are representing A, E, I, O, U. So if vowels are going to be present inside the set, What will be present in the universe? This universe will contain consonants. So we can say universe is equal to the alphabets. So from the alphabets, this set is taking only the set of vowels. The remaining consonants B, C, D, F, G, H all will be staying in the universal side. Let's take the set of odd positive integers less than 10. So here we are representing universe and this is the odd integers. If we say this is going to be odd, apply the concept of all positive integers. It means every number other than 13579 will be covered here. So what happens when there is no element in the set? That is what we call as empty set. Let's take x is a positive integer. X square is equal to 3. Which number when you square it up will give 3? Only root 3 the whole square will give you 3. This is the only possibility to get 3 when you want to square a number. But is root 3 a positive integer? No, it is not an integer. Integers should have negative numbers, 0 and positive numbers. When we say a set is with no elements, then we call it as an empty set or null set. The denotation will be using the phi symbol. The empty set can also be denoted by empty curly braces. If you don't mention anything inside the curly braces, it means the set is empty. So let's take the empty set representation as the set boundary alone. There is no element inside. And this is equated to an empty folder. Just take an empty folder in your system. You will have nothing inside. Just the folder alone will be existing. Similar way, just the set is existing as empty set. Inside that you will have nothing. Next we will see about singleton set. It is a set with only one element. Let's take that element to be A. We will denote it as S is equal to A. It means this set has only one element, which is A. Now we know empty set is denoted as empty curly braces or the phi symbol. If you place the phi inside the curly brace, so this is actually the set and this is the empty set. When we say it is empty curly brace, it is empty set. When we say it is phi, it is empty set. But when you have an element in between the curly braces, it means the set is not empty here. And what is the element present in the set? It is an empty set. You are not worried about what is present inside this set. But you are seeing only that the set is filled with one element. So this single element of the set is the empty set itself. This empty set is what this symbol is denoting, and this single element of the set is what you are seeing on the whole. So let's take the empty set and let's take another set. This is the diagrammatic representation. So there is a set with empty set as the single element, but here this is just the empty set. From this diagram, what do you understand? Both are not equal. When they say set with empty set, it is not equivalent to empty set. That is, when you have phi symbol in between curly braces, that is not equal to the phi symbol without the curly brace. This is for the empty set and this is for the set with empty set. Both the symbols are not same. Let's see it in the context of empty folder. This is what we saw for phi or for empty curly braces. What about set with empty set? So let's take the set here and inside we have an empty set. This is the folder with empty folder. This folder is denoted by curly braces and the empty folder is denoted by phi symbol. What is the other way of denoting this? We know the outer folder is one curly brace. What about the empty folder? That can also be represented by another curly brace. This is the empty set inside. So you can either represent it using two curly braces enclosed with nothing or one pair of curly braces enclosed with phi. Both these notations are actually equal, but these two are not equal. The other way to represent the folder with empty folder is what I mentioned using dual curly braces together. Next we will see about equal sets. Two sets are equal if and only if they have the same elements. So when I say one set is having 1, 3 and 5, the other set will have the same elements. We are not concerned about the order of the elements. We are concerned only about the element themselves. We are representing both the sets using Venn diagram. So let this be S1 and let this be S2. S1 is equal to 135, S2 is equal to 351. Then we can say S1 is equal to S2. We are not worried about the order of the elements. We are not worried about the repetition of elements. All you have to see is both the set elements are same or not. Now we will look upon some popular sets that are available. So let's take the natural numbers or the non-negative numbers. When you say it's a set of natural numbers, it starts with 1, 2, 3. When you say it's a set of non-negative numbers, this will be starting from 0. Usually we have natural numbers 1, 2, 3. Then whole numbers from 0, 1, 2, 3. Capital N can be represented for non-negative numbers, which includes the whole number as well as the natural number. So we will go with this notation. Which category includes the natural numbers? Integers. All the positive category will be present in the natural number. Integers are represented by capital Z. It includes negative number, 0 and positive number. They are called the set of integers. We also have another category which takes only the positive part of integer. So that is denoted by Z plus. Only the positive numbers are taken for the set of positive integers. So when they say it's a universe of integers, it will include negative numbers, positive numbers and 0. When they say it's a universe of positive integers, it will include only the positive numbers 1, 2, 3, etc. What about the next set? We have rational numbers. Rational numbers include integers and fractions also. So when you go above one level, the previous level is becoming a subset to the above level. It is denoted by Q. Q is equal to P divided by Q, and this Q is not equal to 0, which tells that there are possibilities of fractional values. Here P is an integer. The denominator Q is an integer, provided the value should not be equal to 0 for denominator. These are the set of rational numbers. Some examples are included here, whether it is positive fraction, negative fraction or even integer itself, all three are included here. What about the next set? It's about the real numbers. Real numbers include rational numbers and irrational numbers. Capital R will be used to represent the set of real numbers. R plus is used to represent the set of positive real numbers. You have Z, Z plus in the case of integer, R plus in the case of real. So these are completely denoting only the positive numbers. Example of real numbers are given as pi. What is the value of pi? We know it is 3.14. Similarly for e we have a value. Then minus 9 root 2. Next we will see about complex numbers. So they include the real numbers, and along with that pure imaginary numbers are also included. It is represented by C, the set of complex numbers. And here's the example. So we have the imaginary part in complex numbers. Usually imaginary part will be represented using I. So overall you should have idea about all these popular sets. Next we will get into the concept of subsets. Set A is a subset of B if and only if every element of A is also an element of B. The notation is given by this symbol. The description of this notation is A is a subset of the set B. So let's take example. A is equal to 1, 2, 3, 5, 7 and B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the universe of numbers, we are picking B value 1, 2, 3, 4, 5, 6, 7, 8, 9. In that 1, 2, 3, 5 and 7 are present in A. 1, 2, 3, 5, 7 and the remaining numbers 4, 6, 8, 9. These are present in B and the other numbers will be present in the universe. Overall subset means every element of A should also be an element to B. To show that A is a subset of set B, show that if X belongs to A, then X also belongs to B. So just check, A has 1, B also has 1. A has 2, B also has 2. A has 3, B also has 3. A has 5, and B also has 5. A has 7, B also has 7. To show that A is not a subset of B, find a single X that belongs to A such that X does not belong to B. So let's see an example for this. A is equal to, we can have it as 1, 2, 3 and B is equal to 2, 3, 4, 5. Can we say A is a subset of B? No, because 1 present in A which says it belongs to A does not belong to B. 1 does not belong to B. It is not a member of B. Even if one element that is present in A, if it is not present in B means A is not a subset of B. Let's see some examples. X is odd and X less than 10 is a subset of set of all positive integers less than 10. What are the positive integers less than 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. What are the odd integers here? 1, 3, 5, 7, 9. This is what it is given in descriptive form. 1, 3, 5, 7, 9 is a subset of 1, 2, 3, 4, 5, 6, 7, 8, 9. The set of rational numbers is a subset of the set of real numbers. Rational numbers is Q, real numbers is R. So we can say Q is a subset of R. In that case, if you consider all the popular sets, the non-negative numbers is a subset of integers. Integers are the subset of rational numbers. Rational numbers are a subset of real numbers. For every set, phi is a subset of S. It means the empty set is a subset of S. At the same time, the set itself is a subset to S. It includes both the empty set and the set itself as a subset. We know what is a subset. What about proper subset? Let's take the set A and B. You have the same numbers in A as well as B. A is a subset of B because A is equal to B holds true. All the members that are present in A are present in B also. So we can also say the complete set as a subset. So A is a subset of B. Let's take the sets now. A is 1, 2, 3, 4, 5, 6, 7, 8, 9. But B this time has an extra element called 0. When a set A is a subset of B but that A is not equal to B, we will write this as A is a proper subset of B. So the notation is proper subset. So when it is with the equal to symbol, it is the subset. When it is without the equal to symbol, it is the proper subset. What happens in a proper subset? All the elements that are present in A will be present in B, but B will have additional elements. In that case, we can say A is not equal to B. For A is a proper subset of B to be true, A should be a subset of B. This must be true, and there must exist an element of B that is not an element of A. In this example, 0 is in B but not in A. At the same time, A is a subset to B. This is also true. From this, we can take this as, if we can prove A is a subset of B and B is a subset of A, we can say both the sets are equal. Say for example, A is a subset of B in this case. This is true. B is a subset of A. Is that true? Yes, it is true. When both these cases are true, we can say that A is equal to B. This is what they have mentioned here. What about the second example? So let's take this as 1 and this as 2. Here we know A is a subset of B, but B is not a subset of A because B has one additional element. If this is going to be the case, here comes the term proper subset, where we can say A is a proper subset to B. Now we are getting into set as an element. So far we have been seeing elements inside the set as individual elements. Now we will find even set as an element to another set. Sets can have other sets as members. Let's take an example. This set has 4 other sets inside. N, Z, Q, R. What are they actually? Non-negative numbers, integers, rational numbers and real numbers. This is a set containing 4 elements where each of them is a set again. So let's take the set diagram here. Inside that we have 4 sets. So each element is in turn a set. The 4 elements of this set are n, the set of natural numbers or non-negative numbers we can say, z, the set of integers, q, the set of rational numbers, and r, the set of real numbers. So these 4 sets are present inside this particular set. So we can say the set can also be an element to another set. Now we will get into size of a set. If there are exactly n distinct elements in S, where n is a non-negative integer, it means n can be 0 to any number. S is a finite set. It means you can count the numbers of set. N is the cardinality of S. The cardinality of set is denoted by this symbol. The size of the set can be termed as cardinality of a set. What is cardinality? It will count the number of distinct elements in a set. So let's see some example. The set of odd positive integers less than 10. So far we have been seeing 1, 3, 5, 7, 9. That set is taken here. The cardinality of the set is 1, 2, 3, 4, 5. So they have given size of the set as 5. The next example, the set of letters in the English alphabet S is equal to A to Z. So what is the cardinality of this set? It is 26. There are 26 letters. A set is said to be infinite if it is not finite. The set of positive integers is infinite. Let's take the positive integers. It starts from 1, 2, 3, it goes on. Do you know where it is going to end? No. In that case, it is infinite. That's why they say the set of positive integers is infinite. Next, we will get into the power sets concept. What is a power set? Given a set S, the power set is the set of all subsets of the set. The power set is denoted by P of S. What are the possibilities of subset? You have to basically include the empty set as well as the complete set should also be included in the subset part. So let's take an example. How do you find the power set of the set? What are the individual elements here? 0, 1, 2. So the set of all subsets of 0, 1, 2 has to be included. 0 is a subset to 0, 1, 2. Is it right? Yes. 1 is a subset to 0, 1, 2. Is it right? Yes. We have to take the set of all subsets. When you take it as subset, I have to denote it this way. First, I am denoting the elements individually. 0, 1, 2. Then I have to take elements together like this. 0, 1, 0, 2, then 1, 2. This is actually the set S itself. The null has to be included as well as the complete set also should be included. The empty set and the set itself are members of this set of subsets. So definitely you have to include them. The next example, power set of the empty set. Previously we saw about elements inside the set. Now only empty set is given. What is the power set of the empty set? The empty set has exactly one subset, namely itself. What is empty set actually? It has nothing. When you have nothing, what is the only element that you can enter? You can enter only this null. That is what is entered here. Just understand this example based on this example. Here you have placed 0, 1, 2. You are starting with null. You are working with all the elements together and completing the set as it is. This is how we did before. Now instead of 0, 1, 2, we have only empty set here. After that you don't have anything. So you are closing the set with null symbol. Now what is the power set of this set? Empty set is this one, or you can take this to be only null. This is a set with empty set as an element. So this is empty set. Now we have to find the power set. How do you find? You should include null as a subset. Next you have to include the element completely as the subset. In that case you will have null and the set with empty set as it is. Just take, when you have only empty set, power of set becomes a set with null element alone. But when you have a set with null as an element, the power set will basically have null, then the complete set will be included. Why are we including only these two? Because you don't have any other elements inside. So this is the way you have to work with set with empty set and the empty set. That's why I have included both the examples here. For problems involving testing all combination of elements of a set to see if they satisfy some property. For this purpose only we are using power sets. How many elements will be present inside the power set? If a set has n elements, then its power set has 2 power n elements. Let's check. There are actually 3 elements here. So 2 power 3 will give you 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes, there are 8 elements. How many elements are inside? There are 0 elements. 2 power 0 is equal to 1. You have only 1. What about this? You have only 1 element inside. 2 power 1 is equal to 2. You have 2 elements. So this particular 2 power n elements is perfectly satisfying all the 3 examples. Now we will learn about the discrete structures that are built from these sets. Actually, after knowing sets concepts only, you can get into these discrete structures. It is because they are based on the sets concept. Though we may not directly apply sets, only with the understanding of sets you can use them. What is the first one? Combinations. It is called as unordered collection of objects used in counting. The next one is relations. Set of ordered pairs to represent relationships between objects. From the term itself you can understand they make use of sets. The next concept is graphs. When you want to construct some graph, you will be using nodes or vertices and edges. So what are these actually? You have a set of vertices and edges that connect vertices. Similarly, there are finite state machines. You have a set of states totally, set of input alphabets and set of some kind of symbols used in the machine. Overall, they are used to model computing machines. Then we have functions. Are functions discrete structures? Do you have that question? Definitely they are structures of mathematics. Functions assign each element of a first set to exactly one element of a second set. Usually they will say it's a kind of mapping that occurs. One-to-one correspondence, all those things they will say. One side they will have a set, another side they will have a set, and it will be exactly mapping to one element from one side to the other side. This assignment is actually what we term it as functions in mathematics. Don't think it in the perspective of programming languages. This is restricted to mathematics. So in all these cases, we will be using the sets concepts. Now we are getting into the connect. Where does this concept of set connect in computer science? Concept of a data type in computer science is actually built upon the concept of set. What is actually set? What did you understand so far? It's a collection of elements. What are actually data type? It is also a collection of characters. If you take integer data type, it's a collection of numbers. If you take character data type, it's a collection of letters. So it is also built on the concept of set. So what is a data type? This is a name of a set together with the operations that can be performed on objects from the set. If you have some elements in the set, what kind of operations you can do with the set is what you can collectively take it as a data type. Let's take the integer. This is the name of the set. What are the set elements present inside integer? You will have 0, 1, 2. Similarly, you will have negative integers, everything. What are the set operations possible? I am not getting into all kinds of operations. What are the basic operations that you can do with integers? You can add, subtract, multiply, divide. This is exponent operator, the power operator, and this is the remainder operator, modulo operator. Overall, with what are you working in these operations? You are working with the numbers. Where are the numbers from? They are from the set elements. When you say integer, you are restricting yourself only to integers. You are not getting to the fractional parts. At the same time, when you add two integers, you will get another integer. But when you divide two integers, you cannot be sure that you will end up only with integer. So this is not a possibility. But what kinds of operations can be done? using integers, all the arithmetic operations can be done. I am telling you in a very plain way. Let's take another set. So the set elements in Boolean will be 0 and 1 alone. What are the possible operations? Using 0 and 1 we can use 3 logical operations basically, and, or, and not. We will be seeing about this later in this series, but as of now, if you want to do some operation with Boolean values, only these logical operations are possible. Let's take the not. What is not of 0? It is 1. When you say not of 1, it is going to be 0. So this data type concept in computer science is built upon the concept of sets. This sets concept from mathematics has given rise to the concept of data type in computer science. This is what I wanted to tell in a nutshell. Now we are getting into the practice problem session. List the members of these sets. So there are 3 sets given. We have to find the members of the sets. What is the first set? X is the square of an integer. X is less than 100. If you take negative numbers also, they will end up in positive squares. Minus 1 the whole square will give you 1. 1 square will also give you 1. Minus 2 the whole square will give you 4. 2 square will also give you 4. If you want to take the square of an integer, consider only from 0 to 99. So the square value should alone be picked. At the same time, it should be below 100. What are the numbers possible? We have 0 for 0 square, this is 1 square, this is 2 square, this is 3 square, this is 4 square, this is 5 square, this is 6 square, this is 7 square, this is 8 square, and this is 9 square. If you go for 10 square, it will become 100, but it is less than 100, so we are not including 100. Now how will you represent this? The answer will be 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Just equate it to some set A. What about the second one? X is an integer such that x square is equal to 2. Root 2 the whole square will alone give you 2. But is root 2 an integer? No. If x is going to be 1, x square is 1. If x is going to be 2, x square is equal to 4. If it is 0, it is going to be 0. If it is going to be minus 1 the whole square, it is going to be 1 again. Minus 2 the whole square will also give you 4 again. Is anywhere it is equating to 2? No. Root 2 the whole square will alone give you 2. But root 2 is not an integer. When you don't have any element that satisfy this property, what is it? It is an empty set. Both are empty set. What about the third one? X is a real number such that x square is equal to 1. 1 square is equal to 1 minus 1 square is equal to 1. You have two possibilities of getting 1 when you use x square. The set elements will be 1 and minus 1 for this particular description. Next question. Use set builder notation to give a description of each of these sets. So the first one 0, 3, 6, 9, 12. From this what we can understand? It's a multiple of 3. At the same time, the values are less than 15 we can say, since we are going in multiple of 3. Another way is from x is equal to 0 to 4, you are just multiplying 3 into x. This is what we can say. Let's see, x is an integer of multiple of 3 and x is less than 15. This is our first interpretation. The second interpretation is x is equal to 3 into n. The n value will be 0 to 4. 0, 1, 2, 3, 4. 3 into 0 is 0. 3 into 1 is 3. 3 into 2 is 6. 3 into 3 is 9. 3 into 4 is 12. So did we get the same set here? Yes. So it can either be this way or this way. Both answers are right. The next example is minus 3 to plus 3. So x is an integer between minus 4 and plus 4. So usually when they say minus 4 and plus 4, these two ranges will not be included. So there is also another way to say, usually the ranges are not included. If you think the range should be included, then we can just make it as between minus 3 and plus 3. This condition stands better because by greater than minus 4, we will not include minus 4. By less than 4, we will not include 4 definitely. So this stands better. This stands unambiguous we can say. What about the next set M and OP? So this is a direct reference we can say. X is a letter between L and Q. So M and OP. When they say L and Q in description form, it means you have to include only the in between letters similar to this one. So here we can also say between M and P. But in general, when they use between, it means they will not include the extreme ends. Next problem, determine whether the first is a subset of the second is a subset of the first, or neither is a subset of the other. Let's take the first statement. The set of people who speak English, the set of people who speak Chinese, both are different category. Let's take a Venn diagram. C stands for Chinese speaking people, E stands for English speaking people. This is completely separate and this is completely separate. So we can conclude neither is the subset of the other. Let's take the second one. The set of people who speak English. The set of people who speak English with an Australian accent. It means both the sides they know English. So English is taken as the universal part. And what about the Australian accent? Only a few set of people speak them. So we have mentioned A. Whatever comes in the first place is the first one, and whatever comes in the second place is the second one. So if you take this to be A, this to be B, then neither is the subset. If you take this to be A and this to be B, now which is a subset? B is a subset to A. So we can say the second set is a subset to the first set, because the second set is Australian accent English to the people who speak English. Here also they speak English but with Australian accent, but here it's about general English. So this is the E. Australian accent is denoted by A. Next example. The set of flying squirrels. The set of living creatures that can fly. So this is about the squirrels that can fly, and this is about all the living creatures that can fly. Which is the universal part here? Flying creatures are universal part, and the squirrels become the subset. The A set and this is the B set we can take. The first set is the subset of the second set. When you have flying creatures here, inside the flying creatures you have squirrels. So squirrels become a subset to the flying creatures. So the first set is actually the squirrels and the second set is actually the flying creatures. So this is the way you have to interpret. Next problem. Determine whether each of these pairs of sets are equal. What about A? Do you have 1? Yes. Do you have 3? Yes. Do you have 5? Yes. They are equal. Order and repetition does not matter. What about the second one? It means a set has one element. This set has another element and that is 1. What about the next one? The outer set has 2 elements here. But here the outer set has one element. Is this one present here? Yes, it is present. But along with that you have one more element. So they are not equal. The first set has one element and the second has 2 elements. We have to check whether the pairs are equal. When you give repetition of numbers, the set will give 1, 3, 5 on the whole. Similarly, when you give this set, this will have 5, 3, 1. You have to check whether the elements are equal or not. In this case, you have 2 elements to compare. Here this is 1 and this is 1 with curly brace. So both are not equal. What about the third one? Here also they are not equal because this is just null and this is set with null or set with empty set. The first set has no elements and the second set has one element, so both are not equal. So usually repetition does not matter when you take sets. Only the distinct elements will be considered for sets. Next problem. Determine which of these sets are subsets of which other of these sets. If you take 2, 6, you have 2, 6 here. So we can say B is a subset of A. What about 4, 6? Yes, C is a subset of A. Similarly, you have 4, 6 even in D. So we can take it as C is a subset of D. So B is a subset of A, C is a subset of A and C is a subset of D. Here you have only 2, 6. Here you have 2, 4, 6. Similarly, here you had 4, 6. Here you had 2, 4, 6. Similarly, for this 4, 6, you have 4, 6, 8. So this is just an exercise to tell you which set is a subset to which other set. Next question. Determine for which of the following sets 2 is an element and set with 2 is an element. So this is 2 inside a set and this is just 2. First we will check 2, then we will go for 2 inside a set. So let's check for 2. This set has 2 elements and one of those elements is 2. So A definitely has 2. What about B? You don't have 2 here. Both of the elements of this set are sets because it is given with curly braces. Neither of those elements is 2. 2 is actually a number. It is not a set. So 2 is not present in B. What about C? This set has 2 elements again, element 1 and element 2. Both of these elements are sets again. They are given with the curly braces notation. We have to see it in the aspect of A, B and C alone, not what is inside the element. Neither of those elements is 2. So again we have to see 2 as a number, not as a set. So 2 is not present here. Now let's take the set with the element 2. Another element is set with the element 2. So this is present. What about B? Yes, it is present here. So here also it is one of the elements is 2. What about C? Yes, it has this particular element. So all 3 sets A, B, C has the set with element 2, but only A has the element 2. One thing we have to understand, 2 is not equal to the set with element 2. At the same time, the set with element 2 is not equal to set inside a set with element 2. 2 is there, this is one set and this is the second set. But here 2 is there, only one set is there. Similarly, in C, if you take the first element is set with element 2. What about the second element? You have 2, set with element 2. But this is one element and this is the other element. Both are actually sets. Next problem, determine whether these statements are true or false. Both the sets are actually equal, but they are given as proper subset. If there are 2 sets, namely A and B, that are defined under proper subset, A should not be equal to B, but they are equal, so the first one is false. For one set to be a proper subset of another, the 2 sets cannot be equal. What about the next one? This is true because this particular set with element X is completely present inside another set. Set with element X is the only element that is present in the other set. In that case, we can mark this as true. What about X belongs to X? This is false. The only element of the set with X is a letter. It is not a set. When we say A belongs to a particular set, that is meaningful. When they say A belongs to, this is also meaningful. But we cannot take this. That is what is given here. What about X is a subset to X? This is true because every set is a subset to itself. A is equal to B is possible when A is a subset to B. Only when A is a proper subset, A cannot be equal to B. So here A is equal to B. In that case, it's a subset only. So this is true. What about the final one? It's a proper subset they have given. The set, you have 2 curly braces with a phi symbol, is a subset of the set containing elements. What are the elements inside? One is the empty set and another one is the set with empty set. So they are asking whether it's a proper subset. This is true. Set with empty set. This is the only element available here. Is this element present in the second set? Yes, it is present in the second set. So only it is present in the second set. It is not equal also. In that case, we can say it is a proper subset. You just take the left hand side. You have only one element. So this is one element. What about the right hand side? You have 2. One is the empty set and another one is the set with empty set element. Is this element equal? Yes, it is there. The set contains only one element, and since this element is also an element in this, we can mark this to be a proper subset. So in case if they give proper subset of the same thing, at that time we can say it is false because both are equal. In case if they say it's a subset, then it is true because every set is a subset to itself. Next problem, use a Venn diagram to illustrate the relationship. A is a subset of B and B is a proper subset of C. So let's take the universe part and we'll have B first because B is involved in both the cases. We have to say A is a subset to B. So A will be within B. So this will define A is a subset to B. What happens when we say B is a proper subset to C? B is inside C, but it will have an additional point here. This means B is a proper subset to C. Place a dot in certain regions to indicate that those regions are not empty. In the sense, if we say B is a subset to C, B can be equal to C. When we say B is a proper subset to C, B cannot be equal to C. In order to prove that both B and C are not equal, we are just telling that this region is not empty but it has one more element that is not present in B. To indicate that only we are placing a dot here. This is required by the fact that these are proper subset relations. When you place A as a subset of B in Venn diagram, inside B you can place A. When you want to place B as a proper subset to C, inside C you have to place B. But this is actually subset relation. When you keep an additional dot, it means C has one element that is not present in B, which makes proper subset property to be true. This is how you have to represent it in Venn diagram. Next problem, what is the cardinality of each of these sets? What is cardinality? It is the number of elements it has. The number of elements inside the element is irrelevant. Let's take 1, 2, 3. What is the cardinality of the first one? You have only one element here, so cardinality is equal to 1. What about the cardinality of the second one? 1, 2 and 3. You should not count the number of elements in its element. It means you should not count them. It is irrelevant. We have to count only what is present for the outer curly braces. What about the third set? The cardinality is 2. This is how we have to find cardinality. Next question. Find the power set of each of these sets where A and B are distinct elements. How do you find the power set actually? You have to include null, the complete set as well as every individual element. So let's take the power set of the first one. We have only one element. So we are including the null as well as the element itself. Now how many elements are present inside? We have only one element. So 2 power 1 will have 2 elements in total. It is right. What about A, B? You have 2 elements totally. N is equal to 2 means 2 power 2 which is equal to 4. So basically you have to include a null, then you have element A, then you have element B, then you have the element together as A comma B. This will be the set. What about the third one? Here also you have 2 elements, so there should be 4 elements in the power set. Start with null, then you have to go with the first null, then you have to go with the second null inside set. Then you have to go with the complete set that is given. So first make this as a set, this as a set and then together as another set. So this null is made as a set, this null inside set is made as a set, again the complete set is taken. Next question, how many elements does each of these sets have where A and B are distinct elements? When we see the notation is P of something, it means they are asking for the power set. So in power set we have to count the number of elements alone. 1, 2, 3. There are 3 elements. So the power set should have 8 elements in total. What are the 8 elements? Let's take power set is equal to First basically we'll start with null. We have to take the elements individually. So it is A, it is B, then the third one is A comma B. So I have to place it in another set notation. Then I have to combine A, B here. So A comma B. Then I have to combine A and A comma B. So it will be A comma B inside the set. Now it will be B comma the set. So it will be B comma A comma B again. Then the complete set as a whole. A comma B comma the set with A and B. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8. Do we have 8 elements? This is the power set. What about the next power set? It has 4 elements. 1, 2, 3, 4. So the power set should have 2 power 4, 16 elements. So let's start. First we should start with null. Then we can take this as a set. Then A as a set. Then again we have to place a set for the third element. Then for the fourth element already there are 2 curly braces. So introduce 3 curly braces. So the individual elements are taken now. Now we have to pair them up. 1, 2, 3. First one, second one, third one. Now we have to do it with A. 1 and 2. Then we have to combine these two. So 2 pairs are done now. Now we have to take 3 together. 5 A as one set. Then 5 A double curly braces A as another set. So we have done with 5 A. Then we did 5A with this A. Now we have to do 5 with these two A. So this is together a set. Now 5 combinations are over. Now we have to take the 3 A's alone separately. So let's take A, set with A, and set inside set with A. And finally the complete set. 5 comma A comma set with A and set inside set with A. So overall if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 elements are present. So if you are not sure about what is written in the screen, I would like you to work it out in a paper to get a clear idea. Now we'll get on to the third one. So what is the power set of 5? What is actually 5? It is empty set. What is the power set of empty set actually? Inside the empty set you have no elements. So n is equal to 0. So 2 power 0 equal to 1. So power set of empty set will have one element definitely. We have to find the power set of one element. It means 2 power 1 is equal to 2. So altogether 2 elements should be present for power set of null set. So first we will take power set of null set is equal to the null value alone. The power set of the empty set has 2 power 0 which is equal to 1 element. So now we have to take the outer power. Power of the inner power set is power of this particular set. How do you find the power of this particular set? It is very simple. First you have to take the null and then you have to take the set itself. This is empty set and this is set with empty set. Empty set is present inside the set. This set has no elements, but this set has one element and that element is empty set again. This power set will have only one element. We have found that. Substituting that element inside this power set, we are finding these two elements. It has one element, so we are substituting 2 power 1 which is equal to 2 elements on the whole. Let me write it clearly. Power set of empty set. So first we will interpret this. So this is equal to power set of set with empty set. We know power set of empty set is equal to this one. So we are just substituting this inside. Previously we had no element, so it is 2 power 0 which is equal to 1. Now we have one element, so we have to take it in the angle 2 power 1 which is equal to 2 elements. Overall you will have the null will come out first and then the set will be taken as it is. So this will be the power set answer. The last problem, determine whether each of these sets is the power set of a set where A and B are distinct elements. Given a set S, the power set of S is the set of all subset of S. Usually they will give S and they will ask for power set. Now they have given something in the form of power set. If it is a power set, we have to find yes. Now they have given null. The power set of every set includes at least the empty set. So power set cannot be empty. Power set should have something inside. It has to include at least the empty set. We previously saw power set of null is equal to the set with empty set. So this is the minimum power set that we will have. We will not have empty set as it is. So this is not a power set. What about the next one? We have null and A. So can you have two elements in a power set? Yes, there is a possibility. When you have n is equal to 1, 2 power 1 will give you 2. If a set has n elements, then its power set has 2 power n elements. That is what I told here. Power set of this particular set is equal to 5, the set with element A means it has 2 elements which can be taken as 2 power 1. So what is the element that is possible? That will be A. So this is a power set definitely. What about the next one? There are actually 3 elements. When n is equal to 0, 2 power 0 is equal to 1. When n is equal to 1, 2 power 1 is equal to 2. When n is equal to 2, 2 power 2 is equal to 4. Do you have the count of 3 anywhere? Just by seeing this count of 3, you can say this is not a power set. The set contains 3 elements, so this cannot be the power set. So it is not. What about the last one? There are actually 4 elements involved. 4 means the value of n should be 2. It means 2 elements have to be involved here. So if we take A and B as the elements, we have A separately, B separately, A and B together, and the null element all are present. This is definitely a power set. What are the 2 different elements here? A and B. So this is also a power set. This is just a basic introduction, but a very detailed introduction to set concepts. We are yet to see more topics in sets. I'll meet you in the next video. Thank you, viewers.